Hello everyone, my name is Emma. Along with Victoria and Austin, we are the team from University North Carolina, Wilmington. We create a study that model the potential loss value of coastal property in New Hanover County, North Carolina, Wilmington, that due to the sea level rising. Since of the boom of industry in 19th centuries, there has been rapid increase in the concentrations of greenhouse gases and an increasing in the average global temperature. As seen from the bottom graph, there's no significant change in sea level from 1700 to 1880s. But since the 1880s, the sea level has risen by 8 inches. 3 inches in the last 25 years alone, and the sea level are predicted to continue to rise. The primary factors causing the sea level to rise are driven by the rise in the global temperature. Heat will cause a thermal expansion of the oceans. This is compounded by a significant flow of water from melting glacier and ice sheets from the places like Greenland and Antarctica. This leads to several reefs. Our shoreline is going to be eroded from the tide reaching further inland and the washing away soil. This effect of storm will be amplified. A storm drain unable to empty into the ocean, but seawater flow upland. Water table will rise, and with the inefficient drain system, permanent inundation or chronic flooding will be our new normal. Saltwater intrusion is yet another risk, leading to the contamination of water supplies and damage to local agriculture. These risks translate to loss of property damage, and increasing in insurance rates for the coastal area. Our objectives are to identify and quantify real estate within New Hanover County that will experience seawater inundation or sea level rise, to find the potential loss in monetary value of property by zip code and factor based on different increase of sea level change over certain periods of time, and to find what's the difference in property value prediction with or without the sea level rise. And finally, we to create an interactive map to display our result. Our data source, the sea level, was pulled from the NOAA database. Property tax data was sourced from the New Hanover County Tax Department. The sea level projection comes from the Intergovernmental Panel on Climate Change. Property value from Zero Property Database. And last, USGS prediction used to compare our funding.
The variables that we used, first from the Zillow dataset, we used the Zillow Home Value Index, which is the median of estimate and actual home values for a given geographic area on a given day. And that is given by zip code and date, specifically monthly from April 1996 to August of last year. From the tax data set for New Hanover County, we use the appraised total value of the properties, which is an evaluation of a property's value based on a given point in time, taking into account internal and external factors. We also use parcel ID, which is a unique identification number for properties for tax purposes, and that's our common variable we use to merge the data. We use neighborhood and street to estimate missing values, which I'll explain how later on, along with the elevation of a parcel and the number of acres. Originally, we were going to use flood zone, but realized predicting future flood zones is a project in itself, so instead we used different increments of sea level rise given by IPCC, specifically 1 foot, which is linked to the year 2060, and 2 feet, which is linked to 2100. We have several assumptions for this project, the first being that properties that are close to each other have similar values, because the way we estimated missing values for appraised total value was by finding the median value by neighborhood and then by street if that wasn't available. We also assume that the tax parcel dataset and the Zillow datasets are both accurate and reliable, since that's what we're basing our predictions off of. Since we didn't predict future rainfall as part of our project, we're assuming that the amount of rainfall is the same in the future as it has been in the past. And we're also assuming that supply and demand is not having an impact on properties that will not be affected by sea level rise, meaning their price will not increase extra because other homes are being inundated or decreasing in value. A final assumption is that Wrightsville Beach is similar enough to Carolina Beach that it can be substituted by Carolina Beach, since Wrightsville Beach for some reason is missing in the Zillow data, so we couldn't build a regression model for it. There have been several obstacles throughout this project, the first being missing values in variables that we need to make our predictions. Specifically, the appraised total value, which is our response variable to predict, had missing values which we estimated by finding the median value by neighborhood and then by street if the neighborhood wasn't available. Also, there was no zip code variable in the new Hanover County tax parcel dataset, so we used ArcGIS to find the zip code of each parcel. In order to predict the property values with and without sea level rise, we need property data for previous years in a larger range than is available, which is just last year, 2019. We ideally would use data from years such as 2000, 2005, 10, and 15. However, this is not publicly available, so this is why we're using the Zillow data, because it does have past year's values. The only issue with that is that it only gives the median property value for each zip code, and it's not on an individual property level. However, this is what is available, so we worked with what we had. We also realized that in the Zillow data, it does not include the zip code 28480, which is Wrightsville Beach for some reason, and this is why we're using Carolina Beach as a substitute, because we feel that the two zip codes are similar enough to do so. A final challenge was, for some reason, that the Zillow data for the zip code 28428 does not start until July 2005, where all the others go back to 1996. Since 2005 is right before the recession, when we originally fit a linear model to it using the entire date range, it resulted in a line with a negative slope. To fix this, we used a smaller date range that produced a model with more accurate results.
So on to the GIS methods used in this project. What exactly is GIS? GIS stands for Geographical Information Systems, and it is essentially a database management tool for geospatial data. So what does that mean? It means we can merge databases based on geospatial attributes. Take this image here, for instance, we have this red flood zone, and then we have this cyan tax parcel data. In order to merge them geospatially, we would use the intersect tool in GIS, and that would effectively cookie cutter these two layers together. It would merge the tax parcel data along this geospatial line that is the flood zone data. And in the end, you get tax parcel data that's only within the area you want, as well as the flood zone data that you wanted. So it effectively combines these two databases. So what were we going to do with that? Well, initially, we wanted to create an elevation flood zone based model. This was going to involve using elevation data and current flood zones to project future flood zones based off of projected sea levels. This turned out to be incredibly difficult, and the main reason was that different hydrological areas act differently. So in North Carolina, we have barrier islands here, intercoastal waters in between the barrier islands and the mainlands, and then rivers, lakes, etc. All of these areas are going to act differently during a flood event. The barrier islands are going to have a higher elevation of flooding above sea level than the river, and that makes sense intuitively when you think about the wind energy and the wave energy coming from the ocean versus what is getting into the river. So that turned out to be quite complex, and we threw that out. And instead, we went with future tidal zone delineation model. This data was already out there. It's provided by the NOAA, which is the National Oceanic and Atmospheric Administration. They provide sea level data in 1 foot increments throughout the whole United States. And it allows us to see just where geographically the ocean or the tidal zone will be in these foot plus increments of sea level change. So here you can see this is present day conditions, and here is a projected future condition with a certain increment of sea level rise. You can see all sorts of parcels that are inundated by seawater and are now in tidal zone, whereas here they were not. So that's going to cause a significant amount of property devaluation throughout whatever zip code we're working with. The only issue with the NOAA data, or the main issue, is that they don't tie these sea level increments into time or temporally. So we had to take IPCC, that is the International Panel on Climate Change. We took IPCC projections to do that. How did we do that? Well, here you have a graph taken out of one of the IPCC reports. You can see today in 2020, we are about 1/3 of a meter above the sea level of the 17 to 1800 range. So we've seen about 1/3 of a meter rise since then. Now we see these projections here. Red line is representative of a worst case scenario sea level rise, and the blue line is representative of a best case, along with their respective margins of error. But these are tied in the axis here that is a temporal axis. So we can tie these in temporally. Around 2060 is when a 1-foot increment at the worst case scenario occurred. And then 2100 for a 2-foot increment above today's levels, that is. And then we can do similar projections for the best case scenario. Now, unfortunately, this data didn't appear to be available to the public, at least the actual data associated with this graph. So we had to go in with engineering software in order to get the precision that we desired to gather the data ourselves. So we went in and kind of drew lines in engineering software to match the times and the elevation changes up we needed. It was not optimal, but we got the data we needed. And what did we get out of that? Well, here's an example of a model. We've got this blue line, which is zip code data from Zillow over time. This is the projected valuation of each zip code on Zillow. Now, we took a linear regression of that data and we extrapolated that into the future to get a model. We next applied this extrapolation line to our tax parcel data point, which isn't exactly matching up with the Zillow data, but we felt was more accurate. So we moved that projection over to our data point as the start point in 2019, and then we had our model, at least the current sea level model. So if sea level were not to increase more, this would be the projection we would see. Now we had to apply our depreciation in real estate to that model. And what did that entail? Well, we assumed, based off of what we read in literature, that every square foot of land that is inundated by the tidal zone is going to be, we're going to see a 100% depreciation. That is, they're effectively worthless. They do not have value anymore. So we applied that to the parcels which are inundated in the GIS layer, and we can come up with our new model once we subtract that depreciated amount.
To briefly go over our calculations, we first calculated the estimates for missing values of appraised total value by first finding the median value of properties by neighborhood, and then by street for those that had missing values of neighborhood. Then we used the Zillow data to build a linear regression model by using different date ranges in order to find out which ones will produce the most accurate results, which we defined most accurate as being as close to the USGS predictions as possible, and then used that to estimate the predictions of home values in 2060, which is associated with 1 foot of sea level rise, and 2100, which is associated with 2 feet. From there, we merged the tax parcel data with the increments of sea level rise data to find what parcels would be affected by the different levels of sea level rise, as well as what percentage of the parcels will be inundated. From there, we estimated the depreciation of homes that would be affected and made our final home value predictions. Now to go over our results. The plot on the left shows our results for the number of homes at risk by zip code for the years 2060 and 2100. For reference, the map in the center is of New Hanover County and is there to help you see what zip codes are where, and their respective colors match those in the bar charts. I will just refer to the zip codes by their colors here rather than the actual zip code in hopes that it will be easier to follow. The zip codes that have the highest predicted number of homes at risk, the purple and brown ones, are both coastal, which is expected. The green and light blue zip codes, as you can see from the map, are also coastal, but they don't have quite as many homes at risk according to our predictions. Finally, the orange zip code is the only other coastal one, and it has a very low number of homes at risk, but this zip code has a significantly higher elevation than the other zip codes, and we think that's the most plausible explanation for this. Now the chart on the right is USGS's predictions, which we can compare our results to. First off, it has many more homes at risk for the light blue and green zip codes. Our results may be different because for the green zip code, it's missing in the Zillow data, meaning we had to use another similar zip code as a substitute. Additionally, for the red and teal zip codes, USGS did not predict nearly as many homes at risk as our model did. Overall, our predictions underestimated the number of homes at risk compared to the USGS predictions, which can be noticed just by the scale of the y-axis, which here on the plot on the right for USGS, it goes up to 3,000, where our predictions on the left goes up to just 1,500. Here is another representation of our predicted number of homes at risk, in which the larger bars represent a higher number of homes at risk. Overall, the coastal zip codes have many more homes at risk than inland zip codes, which, with the exception of the southernmost zip code, which has a very low number of homes at risk, because, as I said earlier, it has a higher elevation than any of the other zip codes. Now to go over the value at risk, which is the difference between the predicted value of homes with and without sea level rise incorporated, in order to see the property value that would be at risk due to sea level rise. The plot on the left shows our predictions for the value at risk for each zip code for the years 2060 and 2100. You can see that the purple and green zip codes have the most value at risk, and they are both coastal zip codes, so this is expected. The light blue zip code is also coastal, and it's surprising that it does not have nearly as much value at risk as some of the other zip codes. And finally, the orange zip code has the least value at risk, which, as we said before, even though this is a coastal zip code, it has a significantly higher elevation, and that is most likely why it has such a low value at risk. The plot on the right is USGS predictions, which, similar to ours, the green zip code has a large amount at risk. However, unlike ours, the light blue zip code also has a lot at risk and may mean that our model for this zip code is not optimal. This plot also shows that the teal and red zip codes also have a relatively high value at risk, which is similar to our results. Unfortunately, the zip code 28449, which is the orange zip code in our plot on the left, is not included in the USGS predictions for some reasons, so we don't have a baseline to compare that to. Similar to the number of homes at risk, our results have underestimated overall the total value at risk, which can be pointed out by the difference in the scale of the y-axis here, which goes as high as $2 billion in the USGS plot, where our predictions only go up to around 600 million. However, that is where most of the predictions in the USGS plot on the right go to as well, with the exception of the green bar in 2100.
We're using the animation bar chart to visualization of the result of loss value of property by its zip code and to comparison of the USG projection. Next, we create an interactive map to display our result by years 2060 and 2100. As seen from the map, when we click its zip code, there's a lot of value display on the map. There's numbers of home and risk, and prediction median value, and predict total value below the sea level rise, and also the total parcels in its zip code, and also predict the total value with the sea level rise. The most important, we can see the total value at risk.
Overall, our predictions found that the coastal zip codes, which include 28409, 28411, 28428, and 28480, have the most value at risk and the highest number of homes at risk. Compared to the USGS predictions, our results tended to underestimate the number of homes at risk, especially for the coastal zip codes 28428 and 28480, which resulted in underestimations of the total value at risk. This underestimation may be due to the simplicity of our model, since we only used linear regression. We attempted other models such as ARIMA, however, these models grossly overestimated future values. Moving forward, we would try to find a better model that can make predictions somewhere in between what we got using linear and ARIMA models. Additionally, other things we can do in the future are incorporate and predict other factors such as storm surge, fixed floor elevation, and future precipitation. Thank you for listening to our presentation, and we hope that you are all well during this time.